Okay, so what I hope to accomplish today is I want to finish up our talk about separability. I want to get some results. I'm not going to prove a great deal of it, just kind of outline it, and then we're going to get into. I'm going to get into sort of a about as applied as I ever get section on maybe some practical ways to actually figure out what the Galois group of a polynomial is, and even show some adventures from calculus. So let's begin with the following. Suppose we have an algebraic extension f over k. Suppose this is algebraic. Let S be the set of elements that are separable over K. And P the set of elements that are purely inseparable over K. So F, so we've got some of these elements that are separable. Some of them may be purely inseparable. What can we say about this? Well, one, S is inseparable. Well, of course, let me point out that the operative thing here is, of course, the set of elements are all separable. Okay, that's the way we define it. But what's going on here is the set of separable elements actually form subfields. Two, F is purely inseparable. Over S. So what we have here is, of course, and of course, this is all going on inside of F, right? Because these are both subsets of F. This is a field, set of separable elements over K is a field. F is an extension field of that field, and this extension right here is purely inseparable. Three, P is purely inseparable over K. So this extension is purely inseparable. Purely inseparable. Of course, this one is separable. Yes, yeah, that's right. Number 4. P intersect S K. We've seen this before, actually. Elements that are both purely inseparable and separable precisely K. The only missing piece to our earlier observations is this: what happens here? And the answer is F is separable over P. If and only F says P. So if you take, so here's what happens. Let me kind of draw a picture here. S is a subfield of F, and P is a subfield of F. So you can put these two fields together. This is the smallest field that contains both. This is the smallest field that contains both S and P. And of course, this will actually be a separable extension. And this right here, the extension from P to F is separable if and only if F is equal to S, and it's not a proper solution. Finally, if F is normal over K, then S is Galois. Okay. Right, then S is Galois over K, F is Galois over P. Galois purely separable part. And the R K S isomorphic to the automorphisms of F fixed P. Because remember, a field is Galois if and only if it's normal and separable. And so what this says, if of course this one's separable, so if F is normal, it's a normal extension, and this right here is normal and separable, and this is also well, under the assumption that it's normal, this is also normal and separable, and there we go. Note that still here, everybody. Let me put this down here as a observation. I'll put this as a proposition there. And this is the transitivity of separability. If F is separable over E and E is separable over K, then F is separable. So here's an observation that I'll make about this. Notice the separability is transitive, so it goes up like this. But we noticed from a previous homework that Galois is not transitive. So that means that being a normal extension is not necessarily a transitive thing. And probably, yes.
That notation, when you say automorphisms of S over J, why are we not just, isn't that what we define the Galois group to be?
Yes, this is the Galois group of S over K, Galois group of F over P, Galois group of F over K.
So is there some reason for using this notation instead of the notation?
Just to emphasize what's being fixed. No. Okay, yeah. Okay. This next one here, let me get this. Corollary to this. Maybe more corollary to what we're doing. And this will be an exercise actually in your next homework set, which I suspect will be Wednesday. I get it to you. Suppose the characteristic of K equals P and F is alpha. over K. Then U and F is separable over K. If and only if, this is kind of a neat little result here. So this is kind of a little quick trick, if you will, how to check if something is separable. Notice, of course, that this containment is always true. KUC is always in KU, right? The trick is the other direction, and this determines separability. That is to say, if KU is containing KP, then U is separable and vice versa. And the P is important here. The characteristic, the fact that the field's characteristic P is important here, and it's the same P there. So given this result, this allows us to do following. Definition. Thank you for let F be an algebraic extension of K. So this is an algebraic extension of fields, and let S be the subfield of S is separable of K. Yeah, separable. Okay. And from our previous result, I mean, this sounds a little fancier than it is. S is just the collection of all separable elements. So what we have here is we have F. Okay, it's an extension of S. The degree. Yeah, so the degree S colon K so the degree of that intermediate field S over K is called the separable degree of F over K. And it is, we will write this way. As for separable degree, and separable degree is just the degree of the intermediate extension that consists of separable elements. The degree of F over S is called the inseparable. And this is often written as so. This degree here is F S. And this is. So this is just a definition we're going to use. This definition will make things a little bit convenient here. So here is, I'm going to give you, what I'm going to give you. I'm going to give you 3 more results before we get on the Galois thing. I'm going to leave the first 2 for exercises, and then I'll prove the last one. So the first one is, yes.
When you say let S be the what is some built about something okay, or use the choice number to say that there does exist.
No, you don't need anything that fancy. All you need is just all the separable elements. That's from the previous result, because if you take all the separable elements, all the elements, so the extension, yes, it is algebraic. So if you take all the separable elements, that's S. Right. And that's
And any separable extension must be in that.
I'm sorry.
Any separable extension would be below that.
That's right. That's it. That's exactly right. Because S is just all the separable. So here's a first sort of exercise. This is not too difficult actually, and it's probably not too surprising. So proposition. Then and so the separable degree is multiplicative, the inseparable degree is multiplicative as well. By the way, of course, if you believe this, you have to believe the other. Right. So just kind of work through that. And you'll probably get what I mean, but if you believe one, you have to believe the other. Here's something that sort of paints a pretty good picture of what goes on when you look at polynomials. Proposition. Let f and kx be an irreducible monic polynomial. I know we're over a field, so monic doesn't matter so much, but this just makes it more convenient. You'll see what I mean when I write the rest of this result. Irreducible monic. And again, like I said, you'll see in the computation why I make that. Every root of f has multiplicity equal to the end Oh, wait a minute. Right down where the E1 came from. But f of x, what capital F? The splitting field. For F. And E1. Okay, so I need that too. So of course, we know that any polynomial has a splitting field. Suppose U1 is a root. Every root has multiplicity. K U1 and K in separability. So in other words, so I can tell you how this factors. It's x minus U1, x minus U2, x minus UN, all to the K U1, K in separability. And N, that is the number of distinct roots there. UIs are distinct. Just be careful. And N is the separability. So notice, so if in fact U1 is a separable element, so this is kind of an interesting thing to glean from this, then this inseparability degree is just one, and these would all be distinct roots. This is kind of interesting because if you have an irreducible polynomial, if one of its roots separable, certainly they all are, there's a certain symmetry, right? They all appear, all n3 appear to the same power, is equal to the inseparability. And number two, if you look at U1, separability degree, this is set. By the way, this is kind of the third time, I don't know if you've noticed this before, but this is kind of the third time we've come full circle on this. Can anybody tell me what that tells me? I mean, we've seen this actually before a little bit, but what does this tell me about that degree? It should be a power thing, right? It can't be just anything, right? And there's a couple of reasons for that. Number one, we have the theorem that this power is separable. Number two, we have that if we have a finite extension of K that's purely inseparable, then that degree must be P to the n power, right? And certainly, if you join U1, well, let's see, we be careful with that. No, I take it back actually. Yeah, and so, no, what I'm trying to say here, correct, this is not necessarily. In fact, if n is bigger than one, it's not purely itself. Well, there we go. This is a mixture of, you want is sort of a mixture. It's not purely inseparable, and if this degree is bigger than one, it's not separable. So this is kind of a mixture. Let me give you something. How many of you have ever heard of the primitive element? Anybody ever heard of this? You might have sort of noticed this a little bit. Let me give you kind of sort of motivate this. And also this is one of my favorite little separability things. And it's a nice segue into your homework, because I think the proof of this will sort of help you on some of the problems they gave you. One of the first examples we looked at y'all walk there is this extension here, and there are more intermediate fields, but so this is the splitting field. Of this field of Q, right? That's like the first example they gave you. Now, notice that this is generated over Q by these two things, the real cube root of 2, and then these cube roots of unity, which you need to finish it off, right? And I think in my first thing I noted that, oh, we had a basis of this. This is actually degree 6 extension of Q, and it's got basis 1. And then I went through the argument that, you know, it's 1, 2 to 1/3, 2 to the 2/3, and then omega times all of it. So omega 2 to 1/3, omega 2, right? Notice that you kind of needed these to make this basis. 1, 2 to the 1/3, 2 to the 2/3, and then you throw this omega in, and this is actually the same argument we used for the 3 being multiplicative, that this forms basis. You sort of need it. But this is actually essentially the development theorem right here. I generated this by 2 things here. If I'm careful enough and I kind of sort through the elements in this, then I can actually generate that over Q by a single element. So there should be some other basis that looks like this. 1 beta squared. Beta. All right, so I don't have to use the 2 things, I use power of them. Anybody want to guess what that element is? Actually, and you will be guessing, because I only know this with I didn't bother to verify for class, but I only know this a high degree of certainty. Anybody want to guess what the picture might be? Yeah, I think that's a really good choice. If you take multiplying, won't do, will it? Because if you take omega times 2 to the 1/3, they'll just give you 3 things before it comes back to 1, right? But if you take omega plus 2 to the 1/3, I'm willing to bet that'll work. Right? And I know the primitive element theorem. I didn't even have to check anything. I know it's going to work here in characteristic 0, and you'll see why. Theorem 8.4.15. This is called primitive element theorem. This is cool there. Supposed to be a finite extension fields. Let me point out, that of course, this also means that this is an algebraic extension. Finite implies algebraic. The converse isn't necessarily true. One. If F is separable, okay. Then F is F is simple. I want to remind you what that means. That means there exists alpha and F such that F is stable. Number two. F is a simple extension of K if and only if there are only finitely many intermediate. There's this only finitely many. Intermediate. So the first thing means you're taken care of automatically. You're taken care of automatically in the case of separable extensions, right? It's always a primitive. It's always a simple extension if the extension is separable. Notice that this covers characteristic zero completely. So if you have a finite extension of characteristic zero fields, if it's finite and characteristic zero, it's automatically a simple extension. That's how I knew that this one over here had to be a simple extension. Or generally, maybe you're not separable. It's a simple extension if and only if there exists only finite and many intermediate fields. So suppose let's go through this. Let's suppose that F is a finite dimensional separable extension of K. We will also assume K is so I want to make this assumption. Now, we're actually going to see later that if K is a finite field and F is a finite extension of it, then that extension is always separable. And in fact, we have a very, very strong version of primitive element theorem for finite fields, and we're going to see that later. So I'm going to go ahead and assume that K is infinite. So basically, this is generated by finite, so this is finite dimensional extension of K. So it's generated by, say, a finite number of elements and hence a finite number of polynomials. Maybe this extension is not normal. Maybe some of these polynomials that you have in here, some of their roots aren't in there. Throw the rest of those roots in. It's the normal closure, right? So it's the smallest field where it's a splitting field of a set of polynomials that define F. This extension is separable and finite. Okay. So there exists only finitely many inner fields between K and F. Bar and hence between. Because when you take the normal closure, F bar is now separable and normal over K, so it's Galois. It's a finite extension, so it's got a finite Galois group. And if it's got a finite Galois group, the finite Galois group has only finite many subgroups. Well, it's only got finite many subgroups, that means it's only finite many intermediate fields by what we know from Galois theory. So if there's only finitely many fields between K and big guy, then there's certainly only finite many fields between K and smaller, right? Okay. So since the degree of F over K is finite, then we choose U and L such that the degree is max. Right now, of course, the degree of F over K is finite. KU is an intermediate extension, right? And so run through all the possible values U and F and just find a biggest sort of simple extension here, KU over K, biggest with respect to degree, that is. So if KU is F, then we're done. That's F is simple. Now, what if not? There exists a B that lives in F, but not in KU. And of course, as you might guess, you need to try to make a bigger extension. Now consider all intermediate extensions. Of the form B plus AU as A ranges. Okay. So here's our element B that's in F, not in KU. Now, look at all these things as A ranges through all the elements of K. Look at all these intermediate extensions here. Now, our assumption on K is it's infinite, right? And so this gives me an infinite list, right? But I know that there's only finitely many intermediate fields, right? And so there has to be some repetition, right? Because I've got an infinite list, it's indexed by K, but there's only finitely many of these intermediate fields that be distinct. So there exists A, B, and A, where A and B are different, such that K of B plus AU is equal to the field K of V plus B. Everybody agree with that? Now note if you look at A minus B times B, this is equal to nothing up my sleeve, U plus AB minus U plus BB. Because of course these cancel out, and that's just A minus BB. And this is in this is actually in K of U plus A. Oh, yeah. I turned this around here, so my bad. Let me fix this because what I'm doing is I'm just varying this by some sorry answer. It's okay and U plus A. Right. So what I want to do is I want to parameterize in terms of K, not the U, but actually the V that is in F minus K. So this should actually, from this kind of repeat these lines here, this actually K of U plus AB equals K of U plus BB. And then this line right here is the same. Now notice this is in because this thing is plainly in here, right? Because see, there it is. And this thing is in here because these two extensions are the same. So U plus BB is in here, so it has to be in here as well. Everybody okay? So what does this mean? This means that A minus BB is in anybody see what the problem is? Notice that A minus B is not zero. So I can divide out by that. And of course, A minus B is also the K, of course. That's important. Therefore, B is in So we've got V in there. And notice that also U, which is U plus AB minus A times B, is in K of U plus AB as well. So U and B are in K. Therefore, K of U plus AB is equal to K of UB. Certainly K of UB contains this, and since U and B are contained in here, you get the other contained. And this strictly contains K of U. Right? Because B was chosen to be an F, but not in KU. What's the problem with that? You might identify the problem.
We don't carry.
That's right. This extension, the KUB, is actually a simple extension. It strictly contains this, and that contradicts the maximality. KU as a simple extension. So we conclude that F equals KU, and so there you have it. Okay, any questions? Okay, so as promised, this is kind of my favorite kind of little fun section here before we get on the stuff. So you all, I know for a fact, because I've seen a lot of you, have been kind of plowing through this homework and figured out some Galois groups, right? But the polynomials I gave you were pretty specific, right? I mean, they factor nicely, they're a little tricks you can do. What if you're out in the weeds, right? How do you do this in general? I'm gonna give you some techniques. I'm gonna give you some facts that you will need here. And then I'll give you a technique, and I love this, being the pure mathematician I love this. I'm gonna give you a technique that always works. No matter what, it always works. And you should never, ever, ever use it because it's just awful. But in theory, you can compute any Galois group, but it is so computationally out of hand. It's actually kind of fun to see. Proposition 851. Let f of x, okay, x, I want to be separable, so I'm assuming that I can't find Galois groups here. Irreducible polynomial for n. Separable, irreducible, and degree of f is n bigger than or equal to 1. The splitting field is a Galois extension. If f is splitting field, of f of x of k, then f is a Galois extension of degree no more than n factorial. Over k no more than n factorial. What is more, N divides the order of the Galois of F over K. And is a transient subgroup of S. And Galois group of F over K now we've mentioned this before, because any pair of roots, if you join it, they're the same, so there has to be some automorphism that takes one to the other. So there's probably nothing really new here. This is just kind of a warm up, and next time we'll get down in the weeds and get our hands dirty, figuring out showing you some methods and we'll actually do some of this stuff. Any questions? Questions? All right. Well, you all have a good one, and we will see you on